Okay, we have two major topics we're going to cover today. The first topic is violations to the octet rule, and the second topic is going to be how to tell the geometry of the various molecules that we're making. And we're going to use, well, we're going to have violations to the octet rule, but basically in tomorrow's lab, which I forget what the name of it is, it's the Lewis Structure Lab. I think it's actually Lab 11, but I think I accidentally printed it after Lab 12, so you may have to look around in your lab handouts to find it. We're going to be basically building models and practicing drawing Lewis structures. So everything that we did Monday and everything that we're doing today, you're going to get to do in lab on Thursday, which is excellent practice because you also have to do it on the test. So what we'll first start talking about is the exceptions to the octet rule. Then we'll start talking about the shapes of molecules, and that's when we get to play with the fun little models. It's kind of like playing with Legos or Lincoln Logs or something fun like that. It makes me happy to be a child sometimes. So there's basically three exceptions to the octet rule. So one of the things that we kind of broke the lecture down on is every molecule that we looked at yesterday obeyed the octet rule and obeyed the standard normal things, like, for instance, chlorine only makes one bond. But when molecules get bigger, especially when we get down to the third and fourth row where we start having, on the periodic table, where we start having access to d electrons in our elements, then the chemistry and the bonding gets a whole lot more complicated, and we're allowed to have exceptions to the octet rule. So for the most part, we'll probably say about 75% of the time we want to obey the octet rule, and then about 25% of the time we'll look at how to violate it. So the first exception to the octet rule is if there's simply not enough electrons. And this really mostly applies to elements in the second row. So an example of that would be, for instance, if I tried to draw the structure of beryllium hydride, so BeH2. So notice that Be has 2 valence electrons, and each hydrogen has 1 valence electron, so there's a total of 4 electrons. Now, what are the chances you can fulfill the octet rule, which, remember, octet means 8, oops, 8, oops, 8, with 4 electrons? You can't. And so, you know, if you're drawing the Lewis structure, you just have to draw something like that. You can't have any more electrons. It can't obey the octet rule. There's just too few electrons. Another example of that would be, for instance, BH3. So boron has, oh gosh, 3 valence electrons. Hydrogen has 3 valence electrons. So you have a total of 6 electrons. And the only thing you really can do is make a molecule like that. Now, here's where we go from black and white, meaning it's pretty obvious that you can't make an octet rule, make an octet, to some gray area, meaning, unfortunately, when we violate the octet rule, it's not always clear whether we should or should not. So in this class, in general, I'll make it very obvious which molecules you're allowed to break the octet rule on and which ones you are not. Does that seem fair? And then we won't worry about the gray things. An example of a gray area for the octet rule would be, for instance, the molecule BF3. So boron still has 3. Fluorine has 7 valence electrons. So that's 21. That's 24 electrons. So we ought to be able to make, have octets, right? We've got lots of electrons around. But if I draw this very simplest structure and I put boron in the middle and I start filling octets, I run out of electrons at that point. And so boron is not happy. And so our normal result for that was to share more electrons. But the problem is fluorine likes its electrons, meaning it's the most electronegative element. Therefore, it's the least likely to ever share. And so the alternative structure for that would be something that looks like this, where we share one set of electrons and I'll leave you guys to do the math, meaning you can double check, make sure this all adds up to 24 and stuff like that. This leaves us with formal charges, is in that boron has an extra electron that it doesn't want, and fluorine has a +1, or it's kind of giving up an electron it doesn't want to lose. And so, you know, this violates the octet. We can argue that this violates common sense. And what we mean by common sense is that fluorine doesn't want to lose an electron. Boron honestly doesn't necessarily really want an electron. And so, which one is more stable? More stable, or more accurate, perhaps we should say, is a question of doing computer simulations. Meaning that we don't have a theory. We will not even come close to discussing a theory which allows us to pick which of those structures is better. Whether it's better to not fulfill the octet rule, or if it's better to break the octet, or to break the octet rule. And so we can't tell the difference between those two structures, which one is best. And it turns out that in real life, we pretty much don't see either one, but you will occasionally see a BF4 minus anion, which allows us to, you know, complete our octets and make everyone happy and still not have fluorine with a positive charge. So again, some gray area. So this would be like on a test, I would simply say the following 4 molecules break the octet rule, draw them. And so you would be allowed to break the octet rule, right? And the other part of the test would be simply all these molecules obey the octet rule, make sure you obey the octet rule when you draw them. That there should be some manner of drawing them that allows you to obey the octet rule. So not enough electrons is a really easy way to violate the octet rule. The other one is, it almost has to violate the octet rules, is if we have an odd number of electrons. Now, one of the things about these first two violations of the octet rule is there's honestly not that many molecules that really violate the octet rule. Meaning, there's not very many good examples of these first two rules because the way they're violating the octet rule is pretty special, meaning not enough electrons, or certainly there's not very many elements that have odd number of electrons. An example of this would be NO, where nitrogen has 5 electrons, oxygen has 6 electrons, therefore there's 11 valence electrons. And so the best you can do is sort of N double bonded to oxygen, and then have an odd number so that here oxygen has 8 electrons, it's happy, but nitrogen only has 7 electrons, therefore it's not happy. And you know, whether you decide that the nitrogen should have an odd number of electrons or the oxygen should have an odd number of electrons, or if you try to do something even funnier, which is make oxygen have, say, 9 electrons and nitrogen have 8, so share some more electrons or something weird like that, it's pretty tough to tell. And these tend to be very reactive, or so very unstable, highly reactive. And they tend to want to form what are called radicals, which is, for instance, the NO minus anion, where it has that, oh, actually, never mind. Well, let's just rephrase that. So they're very unstable, highly reactive. They're called radicals. So basically, they're compounds with 1 unpaired electron. And almost the entire branch of chemistry that makes plastics and things like that makes use of these free radical or this radical chemistry, meaning it's an entire branch of chemistry that you can actually study. You can take an entire semester or year-long course on it. So those 2 exceptions to the octet rule are pretty specialized. You won't run across those very often in your book. You won't run across those very often in class. The last violation to the octet rule, number 3, I guess this technically was number 2, is what we call expanded octets. And these are fairly common, meaning it's pretty easy to come up with a lot of examples of this. And what we mean by expanded octets is it's only allowed for the central atom. So what that means is the atom in the middle. The central atom tends to be, or it tends to occur if the outer atoms, or another word for that we sometimes say is terminal, meaning the ones on the outside of the molecule that aren't connected to more than one thing, are highly electronegative. What that does is it kind of sucks electrons away. Because remember, electronegativity is how much they want the electrons in a shared bond. So the idea is it might look on paper like your central atom has more than 8 electrons, but the amount of time or the way the electronegativity affects the atom, those electrons really don't spend as much time around the central atom as they spend around the outer atoms. And so in that case, it's not like it has more than 8 electrons. And the other part is that that central atom has to be basically a nonmetal, or mostly nonmetals below row 3, meaning they have access to d orbitals. Meaning, if you look at the energy between energy of, say, a 4s, a 3d, and a 4p orbital, they're all about the same. And so atoms really have access to those d orbitals, and they can make then more than 4 bonds. And you can actually get up to, I think the record is like, certainly you can make things with 5 bonds. I'm not sure if you can make 6, because 6 would be 12 electrons in your outer octet. 5 bonds would be 8 or 10 electrons in that octet, and so that gets pretty hard. Some good examples of that would be something like, say, I don't have a lot of good examples written down here. I guess I see how I organize my notes. I kind of mix things up. Let's take a look at, say, PCl5. So chlorine has 5 times 7, or 35 electrons. Phosphorus has, what, 3 valence electrons? And so that gives me a total of 38 electrons. And if you take a look at it, there's no way that you can make an atom. I mean, that phosphorus has its octet, right? So where are you going to put the 5th chlorine? Well, I'll be honest, chlorine tends to not make more than 1 bond terribly often. And so that's not a good way. And so what we end up doing is we violate that octet. We make chlorine have 5 bonds. So now I've used, what, 2, 4, 6, 8, 10 electrons. So I have 18 electrons left. So 35, 28. Good grief, Jay. Do some math. 38 minus 10 is 28, right? Yeah, good. 1, 2, 3, 4, 5, 6, 7, 8, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. What's wrong? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. No, I know, but it seems like I'm running out of electrons, and I shouldn't. So I must have done something silly. Phosphorus doesn't have 3 valence electrons. Phosphorus has 5. It wants 3 electrons to get an octet. That's what I was thinking. Sorry, that's me being silly, because it really should look like that. So that really makes it have 40 electrons. Oops. Minus 10 electrons in bonds. Means I have 30 electrons to fill octets. It makes sense that each 5 chlorines times 6 electrons apiece, that's 30. Then we're done. So notice that according to this, phosphorus has 10 electrons and should be unhappy, but what that really means is it's an expanded octet. And so we're allowed to do that. Phosphorus has the ability to use those d orbitals, and so it's possible for it to make a 5th bond. And you can even have examples of where things make a 6th bond, like for instance SF6. Well, here's 6 times 7 is 42 electrons. Sulfur has 6, so that gives me 48 electrons. And so notice that you almost have to since you can't make fluorine-fluorine bonds very easy, you have to put all 6 fluorines out, and then, you know, we complete all their octets. Then we get sulfur that has actually 12 electrons, and that's again in its expanded octet. But remember, those electrons spend more time around the fluorine than they spend around the sulfur. So the fluorines have like an excess of negative charge. The sulfur has a little bit of a deficit. And so it's not like it really has 12 electrons around it full time. It probably feels more like it has about 8 electrons around it full time. So that makes it happy. So we can have those expanded octets. And then again, there's this gray area. And again, I will illuminate the gray area, making it black or white by letting you know whether you're allowed to violate the octet rule or not. An example of this is the, say, PO4 -3 anion. So if I take a look at it and I have to obey the octet rule, then I have to draw a molecule that looks like this. And each of the oxygens has 6 electrons around it. And we'll put it in brackets because we have an extra 3 electrons. And then we'll go ahead and we'll put in the formal charges. And again, I'm shortcutting a lot, right? It would take you some, math in the equation to figure out the formal charges on your own. It takes some work. Each of the oxygens is a -1, and the phosphorus turns out to be a +1. Or, if we're allowed to violate the octet rule, we can make and form a double bond with one of the oxygens and put a bunch of valence electrons around it again. And again, it has a -3 charge, and we'll put the formal charges in red. So in this case, now I have a -1, -1, -1. So this says that this one's more stable because it obeys the octet, but it has high formal charges. This one violates the octet, but it has low formal charges. So which molecule wins? Well, again, we have to do computer simulations to determine that, and the computer simulations basically say that, let's see, I think it says this one wins. Winner by a small amount. So beyond us to do. We're certainly not going to be whipping out and doing any computer simulations for any of these. So if I had this question on a test, you would write the structure that obeys the octet rule because it would be in the section that we say obey the octet rule. So when in doubt, obey the octet rule. When told to do otherwise, feel free to violate the octet rule. I'll make it very clear again, black and white. We don't want to make chemistry too hard. Okay, so do you guys feel pretty comfortable writing Lewis structures? Have you started in on the homework? Has anyone started the homework? One person? So the lab tomorrow will be all about drawing Lewis structures. So I'm going to force you to get practice doing it. Fair enough? And I got to be honest, I won't say half the questions, at least a third of the questions on the test are simply draw this frickin' Lewis structure and tell me the shape and the bond angles and all the other stuff. So the next thing we want to talk about then is geometry. So this is almost pure math and visualization. And what we want to look at is what shape do molecules have? And the theory that's used to describe this is called valence shell electron pair repulsion theory. It's my favorite. Valence shell electron pair repulsion theory, Vesper theory. I don't know why I like that. It just just sounds nice. It sounds complicated, and you can scare people with it and say, oh yeah, we talked about valence shell electron pair repulsion theory. But honestly, despite its intimidating name, electron pair repulsion, it's got to be one of the most simple, logical, wow, that really makes sense theories to me. Especially if you are pretty good at visualizing things in your head or play around with these little models here. And all valence shell electron pair repulsion theory says is that basically electrons repel each other. Therefore, they stay as far apart as possible. I mean, that makes sense, right? Valence shell is simply saying we're talking about the electrons in the valence shell. Electron pair repulsion simply says electrons don't want to be next to each other. So they're pairs of electrons that are not, in bonds not being shared want to stay as far apart as possible. So the theory name almost tells you what it is, valence shell electron pair repulsion theory. And what it simply allows us to do is determine the shape of molecules. So on the handout I gave you, or in the new version of the book, this is just table 7.4 that we're really going out. What is it called in the handout I gave you? Is it the same? Yeah, it's still the same table. They just shifted what page that table is on. And what we're really going to do is we're just going to build that table. Whether we build it from the bottom up or the top down, it doesn't really matter. It's kind of up to you guys. I tend to start at the bottom. So if we take a look at it, a good example of a molecule that is linear, and this is one of those things where I don't like to make up examples, so we'll just do it, is I can have, for instance, BeCl. And the idea is that we can describe the shape of that molecule as simply being linear. But if I build the molecule, it literally looks like three atoms stuck together in a linear arrangement. And there's a couple different ways that we can get linear molecules. We can do it with violating the octet rule and simply having two atoms bonded to a central one, which arguably I'm missing the central atom. And we'll steal this. My models, when I moved, I don't know, the models all got thrown in a box and they're kind of all over the place, so we'll just steal parts from them. So that's linear, right? And it makes sense. The furthest apart that I can keep those electrons is 180 degrees, right? So the bond angle is 180 degrees. Now, I should point out that when you're doing this, there's two ways that you can go about this. You can simply memorize table 7.4 in your book, and you'll get lots of practice on it in lab in the next 2 days. Or, I got to be honest, there's sort of a logical way to think about it. And you always get the models for this. And really, can you figure out any way to not say that's 180 degrees? I mean, to me, the model means I don't have to memorize that a linear molecule has a 180 degree bond angle. I can physically see that. The other ways that you can get bond angles that are 180 degrees are, for instance, if you have a series of double bonds in a molecule, that gives it a linear structure. So for instance, carbon dioxide has this linear structure like this. So when we build the models, notice we've got these little flexible bonds to represent the sharing of two sets of electrons between atoms. And that again gives us that 180 degree bond angle. The other way to do it is with a triple bond. For instance, if I take a look at this molecule where there's a triple bond between the carbons and the hydrogens, that also gives us a linear molecule like this. And again, if you built that structure for the test, meaning you're allowed to play with the model kits on the test, you don't have to do this mentally in your head, is there any way to mistake that for being linear? No. One of the things I like about the models is they make, instead of having to look at that table and being daunted by it, really the only thing you have to do is remember the special names from the table, and then the rest of it falls apart. So if I have two sets of bonds with atoms, then I can make linear molecules. That's the simplest category. There's 3 different ways that I can make a linear molecule, though. And as we get more complicated, we're going to have more complicated shapes. The next set of things have either 3 sets of electrons, or I'm sorry, 3 bonds. So, well, let's do this. Number of bonds is 3, and the number of lone pairs is 0. And a good example of that is that BF3 molecule we talked about. So notice that it has the 3 sets of electrons that are forming bonds. And if I take a look at that and try to build that in space, what's the furthest apart that I can keep 3 sets of atoms? Looks like a triangle, right? So really I shouldn't draw it kind of like that. I should instead say it's more triangular in shape. And what do you think the bond angle is between these? Yeah, because we know that a triangle, or in a circle, all 3 have to add up to 120, or 360, and 360 divided by 3 is 120, right? This is called trigonal planar. And there's 2 ways you can get a trigonal planar molecule. You can get it from having 3 bonds and 0 lone pairs, or you can get it by having a molecule that has a double bond in it. For instance, if we take a look at formaldehyde, it has 3 sets of bonds, meaning there's bonds between 3 atoms. So that also gives us that trigonal planar molecule. Make sense? And then the nice thing is all the other shapes that are derivatives of it are simply taken or formed by ripping off an atom. So what happens if I rip off one of these atoms? Have I changed the bond angles? So if I now have 2 bonds and 1 set of lone pairs, so the little gray thing is representing a lone pair of electrons. Have I changed the bond angle? Slightly. So the idea is if I take a look at a good molecule for this, SO2, and so if I draw SO2, I get something that looks like this. Sulfur has a lone pair of electrons. There's a double bond to one of the oxygens. Must look like that. So the idea is that this bond angle is slightly less than 120. These 2 bond angles, where the lone pairs of electrons are going to be slightly more. But in class, we're just going to say that they're all 120 degrees, meaning we're going to recognize that, yeah, there's minor deviations from that. So one of the angles might be, 110, and the other 2 are 125, if I did my math right in my head. But we're going to just say that that averages to 120, right? So realize when we talk about bond angles, we're always talking about the idealized bond angles. And you'll notice in your book that they might have the molecule that has, like I said, 110s and 125s. We realize that that is the idealized 120. We have a special name for that, and that is called bent 120. So it's a bent molecule, and the bond angle is 120. Now, if you build this, is it pretty easy to see that that looks bent? Right? And is it pretty easy to see that the bond angle would be 120? So do you need to memorize all this? Well, you do kind of have to remember the name bent. But if you practice building enough of these models and you draw enough of these, what you'll find is that they kind of make sense after a while. So there's 2 families or 2 ways that I can basically have 3 things bonded to an atom. So the next one up is things with 4 bonds. And so number of atoms bonded can be 4, and then we can have different numbers of lone pairs, but notice that the always adds up to 4. So I can have 4, not 4 again, 3, 1, and I can have 2, 2. So here's where it gets a little tougher. We're going to call this a tetrahedral. And a good example of this is just methane, so carbon with 4 hydrogens attached to it. From the picture I drew, what does that bond angle look like? On paper, it looks like 90 degrees, right? But what we have to realize is that in 3 dimensions, the furthest apart I can keep 4 things is what's called the tetrahedral shape. And that bond angle actually turns out to be 109.5 degrees in 3 dimensions. One of the nice things about the molecular model kits is they make visualizing 3 dimensions very easy because they really are 3-dimensional. One of the bad things about paper is 3-dimensional is a pain in the ass to try to draw for some of this. The best you can usually come up with is if you make something that looks like this, where you kind of exaggerate, you know, the bond angles, and then try to imagine one of them projecting back into the paper and one of them projecting out of the paper. There's a lot of ways to draw it. I'm not going to be picky about it. If you draw it with 90-degree bond angles, and then when you're asked what is the real bond angle, you say 109.5, we're golden. So 109.5. What's 360 divided by 4? Is that 109? No, it's not. What is it? I don't even remember. Anyway, getting off topic. What? 90. So yeah, it doesn't really work. I was thinking the math might work, but we have to remember we're in 3 dimensions. Okay, now the idea is that if I rip off one of these, that was tough. Now I have 3 atoms bonded, right, and 1 lone pair. We're going to call that shape trigonal because it looks like a triangle. But instead of being in a plane like this one, right, these look almost alike, don't they? What do you notice about this one? They're actually pointed down. So we tend to call that pyramidal. Middle. Good example of that is ammonia, NH3. It still has the bond angle of 109.5 because it still comes from that tetrahedron, but realize that the bond angles between the atoms down here are probably going to be slightly less, and the bond angle between an atom and a lone pair is going to be slightly more. So again, that 109.5 is the idealized bond angle. And then what happens if I rip off one? Well, I should also point out that notice this is 120, this is 109.5. Pretty hard to distinguish, but if you kind of line them up, you notice that the atoms are slightly off on that bottom one. And so I don't know if you can tell just by looking, and so at some point you'll have to kind of pay attention to the difference between trigonal planar and trigonal pyramidal. They're pretty easy to get confused. Now, if you build the models, is it easy to confuse them? Not so much, I think. Okay, what happens if I rip off a second atom? Well, now I get this 2-2 case. We're going to call this bent 109.5. And the reason we call one bent 120 and one bent 109.5 is because we have to be able to tell them apart. If we just call them both bent, it doesn't tell me whether I've got 2 atoms and 2 lone pairs or 2 atoms and 1 lone pair of electrons. Now notice, does that look almost like the same bond angle too? It's pretty hard to tell 120 and 109.5 apart, right? They're pretty close. And so again, let the model kits help you decide those things. And then just remember that if it's got 3 things attached to it, or came from something that has 3 things attached to it, it's 120s. If it came from something that had 4 things attached to it, it is 109.5s. Now, if I rip off one more electron, I don't really have a shape, do I? Because I only have 2 atoms. So that's not a shape. So we can only rip off so many electrons, or I should say we can only rip off so many atoms and have so many lone pairs. You don't have a case where you have 1 atom bonded and 3 lone pairs. So that's our tetrahedral family. The next one's kind of weird. So if we take a look at number of atoms bonded, here notice the totals are going to add up to 5. So I can have 5 atoms and no lone pairs. I can have 4 atoms, 1 lone pair, 3 atoms and 2 lone pairs, or I can have 2 atoms and 3 lone pairs. Yeah, there's lots of possibilities, right? The table, to me, I don't know, sometimes I think it looks daunting. Sometimes I think once you start playing with the model kits, it's actually really easy. As long as you kind of remember the names, and then most of the names, if you kind of look at the shape in 3 dimensions versus a piece of paper, it kind of, you know, comes out at you. For instance, the base shape for this is called trigonal bipyramidal. Oops, I got that little dyslexia going on or something. Bipyramidal. So notice that we called this shape where we have, you know, 3 electrons in a triangular shape, trigonal planar. We called one of them trigonal pyramidal. This is trigonal bipyramidal because if you take a look at the three in a triangle shape, then you've got one little pyramid that's pointing up and one little pyramid that's pointing down. Now your book has a lot better geometry shapes for this. In fact, one of the reasons I really like this book is this book has a shit ton of good pictures. So go ahead and make sure you read in this book, section 7.9. It's really very good. And what you'll also find is that this is a lot easier if you just take the models and play with them. It's actually why I brought the model kits if you wanted to build them. So trigonal bipyramidal, a good example of that is that PCl5 molecule. And so sometimes we try to draw like those three are supposed to be in the same plane, and then there's one above and one down it. And for the bond angles on this is where they start to get more complicated. The ones in the plane are 120 degrees, but the ones that are out of the planes are 90 degrees. So we don't tend to worry about the bond angles quite as much. So 5 is trigonal bipyramidal. Now what happens if I rip one of these sets of electrons off? Now I have two choices, right? I've got the ones that are in this plane, and I've got the ones that are above and below. Which set of electrons is the best to remove? Or I'm sorry, which atom is the best to remove and have a lone pair of electrons? Should I pull it like this and have this shape, or should I pull it off the top and bottom and have this shape? Yeah, the first one, because I'm pulling one of the ones that has the 120 degree bond angles, right? So that's the electrons that are furthest apart. That keeps the most number of electrons the furthest apart. This is my favorite shape. It's called seesaw. And honestly, if you build a model and set it on your board, set it down, what does it do? It's a freaking seesaw. I mean, it doesn't get any easier than that, is it? And you know, an example of that is, for instance, if I have SF6 where, you know, I've got, or SF4, I mean, sorry, and I've got a lone pair of electrons on one of the atoms and then a fluorine here and a fluorine here. Now, if I just draw that on paper, I don't know if that leaps out at me as a seesaw. It certainly does leap out at me if I build the model, though. That's why, again, you get the models on the test. I won't say this is one of the easiest tests necessarily, but if you practice building these models, I think this test is one of the funnest tests just because you get to play with them. See? Seesaw. I guarantee you'll have a seesaw on the test just because I like seesaws. It's my favorite one. Now, what happens if I rip off one more? The logical one is to take a 121. What does this look like? Again, this one's like a no-brainer. What letter does that look like? Yeah, it's called T-shaped. Again, a no-brainer. Or at least to me it is once you build the model, right? Now, if you don't build the model, is it a little bit tougher to tell? Certainly. An example of this is a really funky molecule. If we have chlorine trifluoride. And it's weird because chlorine is definitely violated in octet, plus chlorine tends to not, you know, want to have or share too many electrons. But you can make a molecule like that. And notice that it's missing the two pairs of electrons, and so it gives me my T-shape. Now, this one's stunning. This one's going to just be way out there. If I rip one more off, what does this look like? Yeah. So this last shape is linear. We rip off the ones that are on the axes, and an example of this is just I3 molecule. And we've got, oops, not I3 down there. And we've got 3 sets of lone pairs. And in order to make that, we have to have a -1 charge. So it looks like you have to memorize a lot of shapes and a lot of shape names. But I got to be honest, half the shape names are just freaking obvious. I mean, seriously, if you call that something besides linear, I'm probably just going to make you eat the model. Have fun pooping that out is all I got to say. Not pleasant, I'm imagining. It's pointy and... No, I'm just guessing. I've never actually eaten anything like that that I had to poop out as a kid. Like, you know, some people tell me, oh yeah, I ate a quarter and I had to poop it out and all this other stuff. Or actually, it's more common for the dog to eat something that you want and then you have to go check its poop. Did they? This explains much about Haley. Any other things that you've eaten that you should not have? Do we have a long list? We'll take this topic up off camera and outside of class, because this could be entertaining. Okay, the last one is if I have 6 things around things. So number of atoms would be 6, number of lone pairs. And here we can have 0, we can have 5 and 1, and we can have 4 and 2. And technically we could keep going, but it turns out that there's no atoms that actually do that. So if I think about what shape, the ability to keep things, six things as far apart as possible, what shape does this look like? It looks like an 8-sided die if you play Dungeons and Dragons. How many people play Dungeons and Dragons? Yeah, what shape is an 8-sided die? It's octahedral. A what? For an atom? Now, I guess, you can probably actually make like buckyballs. You can get all sorts of whacked out. So I imagine you can make a dodecahedron if you try hard enough, maybe. Not in my chemistry class, so that's too complicated. So here what we've got is we've got 4 atoms that are in a plane, and then we've got 1 above it and 1 below it. And in this case, all the bond angles are 90 degrees between all the atoms. That one's 180, I guess, technically, but we're not going to worry about it. So octahedral is pretty easy. Makes sense, right? Now I rip one off. What shape does this kind of look like? Yeah, there's a square, right? And it makes a pyramid. So guess what? It's called square pyramidal. And I didn't really leave a lot of room for it. What happens there is we rip off one of the ones that is on the top or the bottom, and we keep the 4 that are in the plane, although honestly you really can't tell the difference, and there's 1 set of lone pairs. And again, all of these are 90 degrees apart from each other. And the last one, if I rip off one more, what does that look like? Yeah, it looks like a square. So this one is square planar. And an example of that is, now see, this is where we can really get weird. For instance, what do you notice element is in the middle? And what did I say about xenon? It's a noble gas. It shouldn't form molecules, but xenon's got access to d orbitals, and it's actually, I think if I look on the table, it probably has access to f orbitals. When they get that big, they tend to be able to violate some of the rules. So hydrogen or helium, for instance, there's no known compound with helium in it. Neon, I don't think there's one either, but you start getting time towards the bottom end of the table, chemistry gets a lot more complicated. You got a lot more orbitals. The electrons are a lot further away. The energy levels are a lot closer together, so it just makes it a lot messier, and we're allowed to occasionally make, molecules with them. So notice that for shapes that are 4 and below, these tend, oops, I'm missing an atom on this one. Anyway, they tend to make things that obey the octet rule. Anything that makes bipyramidal or octahedral shapes has to violate the octet rule. So figure about 75% of the time, you're going to be looking at the first 5 shapes we talked about. The other 25% of the time is the other 7 shapes that we talked about. So table 7.4, pretty much have to memorize it. Or by playing with these lovely models, you have to be able to derive it. And I don't think it's too bad, because you can just, gosh, that's just square and it's pyramidal. It seems to make sense. As long as you know that that shape exists, it's pretty easy. And boy, the seesaw T-shapes and linears are pretty hard to screw up too, right? So a little bit of memorization that you're going to have to do, but with the practice in lab on Thursday, the practice in lab on Tuesday when you finish the lab up, and the incessant building of models and drawing of Lewis structures will make this seem second nature by the end of it. Okay, let's see. So we mentioned that in class, and it's on the website. I think it's 12, but I'll double check. Actually, no, I think it's 11. This is where I was confused when I apparently made my lab book, and I accidentally put it out of order, if I remember right. So let's see. Yeah, we're doing... Oh, I don't have anything written down. Well, that's horrible, Jay. We're doing, I believe, lab 11. It's called the Lewis structure lab. What?
That doesn't like to update all the time.
You sometimes have to go like this. Refresh, and it should refresh. Meaning it's a browser setting that you have, which is simply some browsers automatically re-download the page no matter what. Some browsers check to see if it's been updated or something, or don't check actually and use a cached copy. So it should update, hopefully, if you always hit the little auto update button, whatever you call that button. I don't know. It's called the refresh button. Oh, the reload this page button, according to Google or Chrome. What? Yeah, F5 too is what I always hit for a lot of things. Yes. So again, it's called the Lewis structure lab because these are Lewis structures we're drawing. I believe it's actually out of order in the lab book. If someone has their lab book with them, they can look. But I think my lab book goes like 8, 9, 10, 12, 11, which is just Jay not paying attention. When he stuck all the files together. So let's see.
Molecular compounds.
Yep, molecular compounds and Lewis structures. It's the last one in the lab book. Excellent. And I think for just about everything, we're almost literally to the end of the chapter. There's only one other, oh no, I mean, we're not to the end of the chapter. I meant we're to the end of the easy stuff in the chapter. What we're going to do next, and we won't do it today because there's no way I'm going to squeeze it in. What we're going to do tomorrow, or Friday, whatever. So Thursday is Lewis Structure Lab. Was that lab? It's the last one in the book. And then today, oh gosh, let's just start over. So today's Wednesday. You were supposed to have for sure A and B done. Thursday we're going to do the lab, Lewis structure. And Friday you should have enough information to do homework 7, C, and D. I guess we forgot one thing. We forgot to talk about polarity. And I guess what I'll do is, do I want to do it now? Might as well do it now so you can finish it. So we want to talk about polarity of molecules. Polarity of molecules. So the idea is that there is an uneven sharing of electrons in most molecules. And what that does is it leads to a separation of charge. And we talked about this kind of earlier when we were looking at things, but an example of that might be the HF molecule. And so if I take a look at the electronegativity of this, I believe it's 2.1, and I know the electronegativity of fluorine is 4.0. And remember, what the electronegativity was is how much they want the shared electrons, or how strong or how much they want shared electrons. And what that really means is that those two electrons between the hydrogen and fluorine aren't shared equally. If I really drew what it should look like, I might draw it more like this, where both electrons are a little closer to the fluorine, but they do spend some time around the hydrogen. And your book draws these lovely pictures like this, where it tries to show the electron density as sort of the size of the cloud of electrons around it. And so fluorine has more electron density than that. I find the easiest way is to simply draw it like this, and we use a little delta plus and a delta minus. What this says is that there's a small excess of negative charge. This is saying there's a small excess of positive charge. Or arguably it's saying there's a small deficit of negative charge, right? And what it's simply saying is that the electrons spend more time around fluorine than they spend around hydrogen. And then sometimes you'll see some books do it like this, where they draw an arrow and put a plus sign on one side. This is basically saying is that that this is more positive, and that the electrons are being pushed sort of towards the fluorine. And so I personally prefer this, although frequently that's pretty easy to draw nice, quick, and dirty and fast. It lets you see where the electrons are. And so we have two types of molecules. We can have nonpolar molecules, in which one of kind of three things happen. The first is simply that there is no difference in electronegativity between atoms. For instance, if I take a look at the oxygen molecule, they share electrons, but, you know, the electronegativity, and I guess I can look it up and put real values in. I don't really care what the value is, but what the heck. Oxygen is 3.5. You know, the electronegativity is the same on both sides. So they share the electrons equally. If I take a look at how that electron cloud looks, it's a completely symmetrical distribution of electrons. I can also have a nonpolar molecule if I have a very specific geometries in which the charges either cancel or are opposite, or are symmetrical, I should say. I don't know how to phrase that perfectly. The way I like to think about it is it does not make a magnet. So it's kind of a negative statement, meaning polar molecules look like magnets, nonpolar ones don't. An example of that is, for instance, carbon dioxide. Here we really do have some unequal sharing of electrons, in that the electronegativity of oxygen is 3.5, and of carbon, if I look it up, carbon's 2.5. And so it really means there's a small excess of negative charge on both oxygens, there's a small excess of positive charge on the carbon, and so if I take a look at that molecule, you know, and the electron density, kind of a little bit more, a little bit less, a little bit more. But if I think about it in terms of a magnet, have you ever seen a magnet that has two negative ends and a positive end in the middle? Yeah, it does not exist, right? Therefore, the molecule is nonpolar. It means it won't interact with electric fields, and it also means that what we're going to find is that things that are polar tend to have very strong interactions with water, dissolve very easily. Things that are nonpolar tend to not dissolve in water terribly easy and don't interact very well with it. An example of something that's dipolar, and we might as well bring it up, that means that there's a separation of charge, whether it's a full charge or partial, and that what it means is that it looks and behaves like a magnet, meaning there's a positive and a negative end. And the classical model for that is water. If I draw the Lewis structure for water, we always draw it bent like this. And if you remember your shapes, that's simply a bent 109.5 degrees. And if you take a look at it, these are slightly positive, these are slightly negative, these are negative. Now, it's a little hard to visualize on paper. So for instance, let's just build a water molecule with these. Notice that if I orient it like this, the positives are on one end, the negatives are on the other, right? So three-dimensionally, if I try to draw that, maybe I should draw it like this. Here's my hydrogen, here's my hydrogen, here's a lone pair, here's a lone pair. And then when I try to think about that in terms of a magnet, one end of this molecule is slightly positive, one end is slightly negative. So what that means is that one water molecule is attracted to another water molecule. One of the things that makes water unique is the concept of hydrogen bonds. That's when we have hydrogen bonded to a molecule and there's that separation of charge, that means that it's kind of an extra strong attractive force. And for instance, if you think about it, or you follow periodic trends, molecules like sulfur with two hydrogens, so SH2 and various other things, those don't have very strong attractive forces between them. They're all gases at room temperature. Water at room temperature is what? A liquid. That's because it's got stronger attractive forces between it. If you look at a lot of other values for water, things like density, if you look at specific heat, and a couple other things that we'll look at in the future, water is always the exception to a lot of those rules. Its value is exceptionally large due to the attractive forces between water molecules. That's chapter 10, though, probably next semester. Oh, I didn't quite get the little positive part. Thank you. That would confuse someone potentially. So the idea is that we can classify every one of these molecules and every one of these models as being polar or nonpolar. For instance, if I take a look at a straight tetrahedron shape, polar or nonpolar? If I drew it, it would have a magnet that looked like it has 4 positive charges, say, on the outside and a negative charge in the middle. Can you have a magnet that's spherical? I don't think so. They might have tricked it and figured out how to do it with like 2 different metals and some weird shit like that, but I don't think you can have a magnet that's like that. And so, for instance, here, because of the bond angles and the way those molecules cancel out, this turns out to be nonpolar. But now if I rip one off, this end of the molecule is always negative, right? Because it's a lone pair of electrons. This is whatever it is on the other side. That definitely has one end of the molecule that's positive, one end that's negative, right? So for instance, a trigonal pyramidal shape always has to be dipolar. Same thing with, we already looked at water, but definitely that end's always going to be negative, right? This end's always going to be positive. This has to be dipolar. So each of the shapes will have a polarity associated with it. Depending upon how the atoms are distributed around it, you can memorize them, kind of, or it's just easier to think about it. Polar or nonpolar? Non, because one charge would be on the outside, the other charge would be on the inside, right? No magnets that look like spheres. Now I rip one off, has to be polar, right? Because this end's always going to be negative, right? This end's always going to be positive. I rip 2 off. What about this? It should be mostly nonpolar because you can't have 2 negative ends to a magnet sandwiched with positives in the middle, can you? I mean, magnets have 1 positive and 1 negative. If you've got 2 ends that are negative or 2 ends that are a positive or positives on the outside and a negative on the inside, those don't make magnets. What about trigonal bipyramidal? Polar or nonpolar? Nonpolar. All these 3 cancel out. These 2 cancel out, right? Now, rip one off, and very definitely this end of the molecule is polar or positive, and this end of the molecule is negative, right? Rip 2 off, same thing. If I look at it like this is all the positive charge, all the negative charge is pointing in one direction. But now if I rip 3 off, is this polar or nonpolar? Nonpolar, because you can't have a magnet with 2 positive ends and a negative middle, right? You can't make a sandwich magnet. I don't know, someone's going to invent one of those someday and I'm going to be wrong, but not yet, that I know of. Although, I really want to Google sandwich magnet right now. So, every time you make a model, every time you draw a Lewis structure, essentially, whether the question asks for it or not, figure out that on the test it's going to say, what shape is this? It's going to say, what bond angle is it? And is it polar or nonpolar? Because those are all the things that we can use to describe molecules and move forward with it. Now, I have to be honest, the way your book is organized, and if we cover the chapters in the order the book is written, we skip and we go to chapter 8, which is all about thermodynamics. Right, Jay? Yeah. And then chapter 9 is about gas laws. And chapter 10, we finally come back to talking about things that are polar and nonpolar. So it's something that you'll probably have to remember unless I decide for some wacky reason to do chapter 10 next, which arguably there's no reason not to do chapter 10 next, except for maybe one thing in it. Realize that you have to remember this polar-nonpolar concept until next semester too. And you have to memorize and remember all these Lewis structure shapes because they start coming back and playing a big role in chapter 10. So you have to, again, remember this stuff over the semester break. Because I highly doubt we'll get to chapter 10. We might, it's possible, but we still got at least another day and a half in chapter 7. Chapter 8's a bunch of days. Chapter 9's a bunch of days. We might get to chapter 10. It's usually a bit of a crunch. sometimes what I do is I skip chapter 9 and we do chapter 10. So realize that the stuff here in chapter 7, remember it for the next few chapters. Okay, I think that's it for me. That gives us all the skills that we need to do the lab tomorrow, and then we'll do that lab on